Welcome to GER Hub Mathematics and Statistics lessons. I'm going to be talking about a course called General Mathematics 2, as you may have it in your school, but we are going to be looking at a particular topic in this live class under General Mathematics 2. And what is that topic? We are going to be looking at functions of a real variable. Functions of a real variable. So that is what we shall be looking at in today's lecture on General Mathematics 2. Okay? So, where do we begin from? The first thing I'm going to be describing in this video is real variable. Okay? So if you must understand this topic, functions of a real variable, it is best we start with explaining to you what a real variable is. Simply put, a real variable is any variable that can only assume real values. Okay? That can only assume real values. Now, what does that mean precisely? If you will check some of my videos on numbers, where I treated rational numbers, natural numbers, integers, and the rest of them, you would come to realize that what is called a real value could be a natural number. What is called a real value could be a rational number. What is called a real value could be an integer. It could be an irrational number. So what we are saying in essence about a real variable is any variable that can only assume real values. It means that a real variable cannot assume complex numbers. Okay? Now, once it is a real variable, it means that if x precisely, if I use x and define x also to be a real variable, it means that the values that x can assume can only come from the natural number system, or the integer number system, or the rational number system, or the irrational number system. Okay, so once x is a real variable, it means it can only assume real values. And by real values, it means x here can assume a natural number denoted by that symbol. X can also assume an integer denoted by the symbol z. X can assume a rational number denoted by that type of q, or x can be an irrational number denoted by this type of f. Now, it means that on no account will x, what is defined in this case as a real variable, assume a complex number. Okay? So what am I saying? If you look through my videos, my previous videos on numbers, you would come to see the details on each of these number systems. Now, what it means is that once something is defined to be a number, if a value is defined to be a number, then it means that that value can either be real or complex. Okay? So this symbol conventionally represents real numbers, while this symbol conventionally represents complex numbers. So, if x is a real variable, then it means it can only assume values that are found in R. Okay? Now, once something is called a real number, it means it could be a natural number. Once something is called a real number, there is the possibility that a real number could be an integer. Once something is defined to be a real number, it means a real number could be a rational number, or it could even be an irrational number. But on no occasion can it ever be a complex number. So, I am trying to explain what this statement or this word is in the particular topic. So what are we looking at? We are looking at functions of a real variable, and it will be best for us to understand this topic to understand this word real variable. So what is a real variable again? A real variable is any variable that can only assume real values. And by real values, we mean that what is called a real variable, in this case, say x, can assume a natural number, can assume an integer, can assume a rational number, can assume an irrational number, because all these put together are real numbers. Okay? Either use this symbol or this symbol. So, having explained what a real variable is, it now means we can proceed. So what next do I want us to discuss? Remember, the topic says functions of a real variable, and we have just explained what a real variable is. But to better understand what a function is, it is good we go straight to understanding something that will lead us to understanding what a function is. So jumping into studying functions will not be good enough except we go through what is called a mapping. So if you want to understand what functions are, it is best we start with understanding what is called a mapping. So the question is, what is a mapping? Now, if you look through my videos previously on set theory, I must have talked about something called empty sets and non-empty sets. Okay? So let us start with defining what a mapping is. Remember, the mapping, our understanding of a mapping would help us understand better what we want to discuss in this topic called functions of a real variable. So to understand this word function, must first of all understand the word mapping. So the question is, what is a mapping? So I'm going to define a mapping for you, but that will start with talking about non-empty sets. So let's do this. Let A be a non-empty set. And by a non-empty set, we mean that there are elements in the set A. So the elements in the set A makes A non-empty. Remember, non-empty sets are sets that contain elements. So if a set contains no element, it will be regarded as being empty. So let A be a non-empty set. Let B be another non-empty set. Okay? So if A is a non-empty set and B is another non-empty set, it means both sets contain elements. So go back to my video on set theory I discussed yesterday in our live class, and you would understand what I am talking about. Okay? So A and B are two non-empty sets. Now, if I present to you two non-empty sets, what then can we say is a mapping? If A and B are two non-empty sets, then a mapping is a rule of association that relates an element X that is a member of A with a unique element, say Y, that is a member of B. Okay? So if there is a rule that associates an element, a randomly selected element, say small letter X in the set A, the non-empty set A, with a unique element Y in the set B, then that rule of association is called a mapping. So simply put, a mapping is a rule, but it will not be wise to end the statement with saying a mapping is a rule. The question is, what kind of rule is a mapping? A mapping is a rule of association that relates an element X from the non-empty set A with another element, a unique one at that, Y from the non-empty set B. Okay? Now, having said this as my first point, let us go to the next point. Remember, we are trying to understand the meaning of the word function, but to understand the meaning of the word function, it is best we go through understanding the meaning of the word mapping. And you will come to see why this is so. Okay? So, having started with this first point that explains what a mapping is, let us now go to the next point. Now, if A is a non-empty set and B is another non-empty set, and we have just defined a mapping to be a rule that associates an element X from the set A with another element Y, a unique one at that, from the set B, what then do we call this set A, from which we have chosen an element X to associate itself with a unique element B and Y from B? What do we call the set A? The set A is called the domain. We call the set A the domain of the mapping. Okay? Now, why is it called the domain of the mapping? It is simply because the elements in A are the ones selected to be associated with unique elements in the set B. So for that reason, it is called the domain. Okay? Now, if A is called the domain of the mapping, what can we then call the set B? So the set B is called the codomain of the mapping. The set B is called the codomain of the mapping. Okay? So we call the set A the domain of the mapping, and we call the set B the codomain of the mapping. Why do we call the set A the domain of the mapping? It is simply because it is from A we are selecting elements to be associated with unique elements from the set B. And why do we call the set B the codomain of the mapping? It is simply because the set B, it is from the set B we select unique elements that are paired with the elements in set A. Okay? So, that is my second point in this particular lesson. Now, let's go to a third point, and I want you to follow me carefully. Now that we know that the set A is called a domain and the set B is called the codomain, there is something important you must know, and that relates to the notation of the mapping itself. Now, we have just said that a mapping is a rule of association that relates elements in set A with unique elements in set B. How do we represent mappings? And that brings me to my third point. Mappings are conventionally, that is by agreement, conventionally represented or denoted with lower case letters. Lowercase letters. So if you want to represent a mapping, or in which case you want to represent a rule of association of elements in A with unique elements in B, it is proper or conventionally agreed you use lowercase letters. For example, in this case, F, G, H, even L, small letter L, etc., may be used to denote mappings. Okay? And I'm going to show you how that is done. Okay? Now, let's go to the fourth thing I would love to say in this particular lecture. Now, let us assume that we chose out of F, G, H, and L. Now that we know that lowercase letters are preferably or conventionally used to represent mappings, let us now assume that F denotes a mapping from the set A into the set B. Now, let us assume that we are using the letter F, small letter f, or lowercase letter f to denote a mapping from the set A into the set B. That is an association of elements in the set A, the domain, with unique elements in the set B, the codomain. How can we represent this mapping F? Okay, so let us assume that F denotes a mapping from the set A into the set B. Then the mapping F could be represented with any of the following descriptions. Okay, so how do we represent the descriptions mathematically? Now, if you want to show that there is a rule that associates elements in the domain X and the domain A with unique elements in the codomain B, then we could use a first illustration, in which case we would simply put the set A, which is the domain, put an arrow moving from A to B, and put the mapping F on it. This is one notation that is popularly used to represent a mapping that takes elements from X and pairs them up with unique elements in a set B. Okay? Now, another notation that is popularly used is this one, where you put F, a colon, A with an arrow going to B. So this is another notation that can be used to represent a mapping that takes elements from A and pairs them up with unique elements in B. If you don't want to use this, you could also use this, a third notation, and this one is so popular, in which case you would simply write Y equals F of X, showing that for every element in X under this mapping F, there is a unique element Y in B. Okay, so for every element X under the mapping F selected from A, there is a unique element in Y, and this is read as Y is a function of X, or Y is a mapping of X. Okay, now let's move beyond this particular point. So these are three popular notations for representing a mapping F, taking elements from A and pairing them up with unique elements in B. Now, that being said, let's go straight into another point. Now, what else is to be discussed? Okay, what else is to be discussed? If Y is the unique element, if Y is a unique element in B, the codomain, associated with an element X in A. So if Y is a unique element in B that is associated with an element in A, then Y is called the image of X under the mapping F. And I'm going to explain this quickly. Now, if Y is a unique element, remember the B set is the codomain and the A set is the domain. Now, what do we call Y, that unique element in B that was associated with any element X in A? The Y is called an image of the element in X, in A, under that mapping F. Okay, so Y is called the image. Now, if you don't want to call Y the image of X under the mapping F, you could also call it Y may also be called the F image of X. So those are two names you could call Y. What is Y? Y is that unique element in the codomain that was associated with the element X in the domain. So Y is usually called the image of that element in the domain under the mapping F, or you could call Y the F image of X. Now, if the mapping was not F, but it was G, then Y will be called the G image of X. If the mapping was not G, but was H, then Y would also be called the H image of X. So take note of that, and let's move to the next point. Now, you will come to see subsequently in my lecture that all the elements in A, the domain, will be assigned elements, unique elements in the codomain. Okay? Now, not every element, if what is being discussed is a mapping, then not every element in B is necessarily an image of an element in A. What that means, the implication of that is that there is usually a collection or a set of elements or images in the codomain that were assigned to the elements in the domain. Now, what do we call the collection or the set of images in the codomain that were assigned to elements in the domain? So that is what I want to discuss. The set of all images of F, the mapping, the set of all images of elements in A, that is the domain, under the mapping, say F, is called the range. Okay? So if you put all the images of elements in A in the codomain together, it will make a set called the range. And what that means is the range is a subset of the codomain. Okay? So what is the range again? The range is a collection or a set of all the images of elements in A under the mapping F. Okay? And for that reason, the range is usually a subset of the codomain. Now, the question is, how do we represent the range? So I'm going to put here, the range is often denoted with the letter uppercase R. This implies that R, the range, is usually a function of the domain. So R is equal to F of A. What is A? A is the domain. Okay? Now, clearly also, you will notice that if R is equal to F of A, since R is a function of the domain, of all elements in the domain, then it means that R, which is F of A, is clearly a subset of B. Remember, what we call the range is a subset of the codomain. And why is it a subset of the codomain? Remember, the codomain contains images. And if you put all the images together in the codomain, not every element in the codomain is an image. Take note, not necessarily. All elements in the codomain must not necessarily be an image to elements in the domain. So if you put all the images of elements in the domain together, you would end up having a set called the range. And for that reason, the range is obviously a subset of the codomain. Okay? Now, the next thing I want to discuss is an arrow diagram. So, usually for us to denote or represent a mapping pictorially, we use what is called an arrow diagram. So, diagrammatically, mappings are described. Diagrammatically, mappings are described with the use of what is called, or what are called, mappings are described with the use of what are called arrow diagrams. So I'm going to show you quickly what an arrow diagram looks like. Okay, so an arrow diagram is a diagram that looks like this. So I can put a set A here, the domain, put this up, an oval shape underneath A, put an arrow that moves from A to another oval shape representing B, and I'm going to put F, the mapping, on top. Okay, so if, for instance, I have in A 1, 2, 3, and I have in B A, B, C, and D. Now, I could take out arrows pairing A and the elements in A with elements in B. So I could have a thing like this where I pair 1 with B. I could pair 2 with A. I could also pair 3 with A. Now, take note of one thing. You would come to realize that this diagram is called an arrow diagram. Why is it called an arrow diagram? It is a diagram that shows the mapping of elements in A with elements in B under F. Now, clearly you would see that F of 1 will be equal to B. F of 2 will be equal to A. F of 3 is also equal to A. And what does that mean? It means that we can draw certain conclusions from what is going on here. And what conclusion can we see? Note the following. Note the following. Note that, number 1, for all x that are members of A, this means this is read as for all x, okay? For all elements x that are members of A, there exists a unique element, okay? So this symbol represents there exists. It is called an existence symbol, okay? And this symbol is read as for all, okay? So for all elements, small letter x, that are members of the domain A, there exists a unique element, y, that is a member of B. However, that is in the case of a mapping. However, not all elements y being members of B must be images of elements x in A. Now, what does that mean? Looking at this arrow diagram, you will see that I have paired the element 1 in A with an element B. So B can be called the image of 1 under this mapping F. I have paired an element 2, which is an element in A, with an element A in B. So A can be called the F image of 2, and the element B, 3 is paired with a unique element A also. So you will notice that A can be called the F image of 3, or A can be called the image of 3 under F. Now, note one thing. You will come to realize that whereas every element in A has an image in B, and note also that whereas some elements in A, more than one element in A, can be assigned one unique value in B. Note, not every element in B, the codomain, must be an image to an element in A. Okay? So that is what I'm trying to explain here, that whereas every element in A has a unique element, or a unique element Y being its image in B, not all elements Y in B must be images of elements X in A. That is the first thing I want you to note. Now, the next thing I want you to note is that R, which is the range, equals F of A in this case, will be the set containing, A and B. And clearly, this set containing A and B is a subset of the domain, or the codomain. Notice the codomain contains elements A, B, C, and D. But what is called the range must be a set that contains only images, strictly images. So, whereas B is the codomain, not every element in B is an image of elements in A under the mapping F. So, take note of that. It is very, very important. Now, let's take an example. Let's take an example quickly of what I've explained so far. Remember, we need a clear understanding of mappings in order to understand what functions are. And I'm going to get to what functions are quickly. So let's consider quickly an example. Let's assume that there is a non-empty set X that contains the first three letters in the English alphabet system. So A, B, and C. And let's also assume that corresponding to this set X, there is another set Y that contains the positions of numbers in the English alphabet system. So this is 1, 2, 3, 4, and 5. Now, I could define a mapping. Let F be a mapping from X to Y. Then I could have a mapping this. I could have this. Using the arrow diagram again, X going into Y under F. Now I would put here A, B, and C, and I could put here 1, 2, 3, 4, and 5. Again, you will notice that A is the first letter, B is the second letter, and C is the third letter. Notice again that not every element of Y, the codomain, is an image to elements in X. So whether or not all the images, all the elements in Y are images to elements in X does not stop F from being a mapping from X into Y. Okay? So that being said, let us now go to the next thing that I want to discuss. Let us now answer the question, what is a function? Okay? What is a function? Now, having known those few things about mappings, having gotten a clear idea on what a mapping is, let us now go straight to what a function is. So, what is a function? Now, remember, this video is a part 1 video to the first topic under the course General Mathematics 2, where I'm explaining functions of a real variable. And I've talked about what a real variable is, and I told you that for us to understand what functions are, it is best we start with explaining to ourselves what a mapping is or what mappings are. Okay? So all we have done so far is explaining the real variable, what real variables are, and what a mapping is. Now, there are certain things I'm going to be discussing in my next video, still on functions of a real variable. Okay, so this is just a part 1 video to the topic functions of a real variable. We will continue this lecture next week. Okay, so what have we done so far? We have explained real variables and we've explained what a mapping is. Now we are going to continue this this particular lecture next week, where we shall be explaining what are the types of mappings. Okay, we shall be explaining the types of mappings in that particular lecture. So stay tuned to the channel, subscribe to the channel, like our videos, comment on our videos, and please share our videos, and endeavor to turn your notification bell on to get notified on when we go live or when we drop videos for you. Okay, so let us round up this video with discussing what a function is, and in our next video we shall go in detail describing the types of mappings and using graphs to explain functions. Okay, so what then is a function? Now, a function, one way to explain or define a function is a function is a mapping, clearly, whose codomain is necessarily the set of numbers or a set of numbers. Okay? So, what we call a function is simply a mapping whose codomain is necessarily a set of numbers. Now, I'm going to explain I'm going to go further into explaining this definition. But looking at it carefully, you will come to realize that a function is like a specific kind of mapping, because mappings give room for relationships between abstract sets But if a mapping is to be called a function, necessarily the codomain must not contain abstract elements. The codomain must rather contain necessarily set of numbers. It must contain numbers. Okay? Now, what does this mean? This means, if you go further to explaining this definition, this means that a function is a mapping which necessarily associates a number x in the domain with a unique number in the codomain. Okay? So when a mapping starts associating numbers in the domain with unique numbers in the codomain, then that mapping can be called a function. Okay? So we usually would represent a function with this notation we had used earlier. And how do we read it? This y, your y in this case will be called the output variable, and because it is an output variable that needs a value of x to determine it, we would call y, this output variable will be called the dependent variable. Again, I'm saying that if f represents a function, now that you know that functions are specific kinds of mapping, what kind of mapping are functions? What kind of mappings are functions? Functions are mappings whose codomains are necessarily numbers. Okay? So we usually would use y equals f of x to represent y as a function of x. That means that y depends on x through f for its value. For that reason, y is called an output variable and specifically called a dependent variable. Why is it called a dependent variable? It is because it needs a value of x to determine what its value will be. And what do we call x on the other hand? X is an input variable that may be called argument. So a name for x, the input variable, is called argument, or you could call it the independent variable. Why is it called the independent variable? It is simply because it needs no value to determine its own value. Okay? So I'm going to be explaining this more in my next class on mappings. So in my next class on functions of real variable, I'm going to be giving examples of functions and giving examples of what are not functions, and I'm going to be telling you about the types of mappings. Do like this video, share this video, subscribe to the channel if you haven't subscribed, and smash a like on the video necessarily, please, to encourage the growth of the channel. And I'll be seeing you in the next live class on GER. Thank you very much, and God bless you.